We're starting Chapter 13, which is about experiments and observational studies. Randomized comparative experiments. An experiment is a study design that allows us to prove a cause and effect relationship. This is the only time in stats that you're going to hear me talk about cause and effect, and that's because the point of an experiment is to prove cause and effect, or disprove. So in an experiment, the experimenter must identify at least one explanatory variable, that's your X, which in this situation we call that a factor. You end up manipulating the factor, and then you have to have at least one response variable to measure. So again, your response variable would be considered the Y variable. For example, if you're testing migraine medicine, the amount of medicine would be your explanatory variable. That's your factor. Your factor is the medicine. You're going to manipulate that. You'll give some people a full dose, maybe a half dose, maybe some people won't get any. The response variable would be how much relief they get from that medication. So in an experiment, you manipulate factor levels to create treatments. So the 3 different doses that I just mentioned, those would be treatments. The full dose, the half dose, and no dose would all be different treatments. You're going to randomly assign subjects to those treatment levels. So whoever was in my study, I would randomly assign who got the full dose, who got the half dose, and who got the no dose. And then you compare the responses from each of the different treatment levels. In an experiment, the experimenter actively and deliberately manipulates the factors to control the details of the possible treatments and assigns the subjects of those treatments at random. The experimenter then observes the response variable and compares responses for different groups of subjects who have been treated differently. Again, this is pretty much what I just said in the last 3 bullet points on the previous slide. In general, the individuals on whom or which we experiment are called experimental units. When humans are involved, they are commonly called subjects or participants, because you're going to get more people to participate if they're called a participant and not an experimental unit, because then it seems like people may actually care about you and are not just interested in the data that you provide. The specific values that the experimenter chooses for a factor are called the levels of the factor. So for example, with the migraine medicine, there would be 3 different levels: full dose, half dose, no dose. A treatment is a combination of specific levels from all the factors that an experimental unit receives. So in the same example, there would be 3 different treatments. There are 4 principles of experimental design. The first one is the control. So the control means that we control the environment that the experiment takes place in. So you want to make as many of the conditions as possible, as similar as possible for all the different treatment groups. So with the migraine medicine, you would want to probably keep people on site, and you would want to keep the lighting and the sound all roughly the same, because sometimes the amount of light and the amount of sound can affect a migraine as well. So you don't want outside influences to have an effect, or at least if they do have an effect, have the same effect across all treatment groups. By controlling the extraneous sources of variation, we reduce the variability of responses. So again, if lighting is going to have an effect, if all 3 groups are exposed to the same amount of light, then that light would have an equal effect on all groups. So by controlling that, we'd be able to see past that specific variable, and it limits the amount of variation that we have. It makes it easier to detect differences among the different treatment groups, and it works to prevent them from affecting the response variable as well. The second principle is randomization. So randomizing allows us to equalize the effects of unknown or uncontrollable sources of variation. So if you have volunteers who suffer from migraines, and some people are going to be more severe than others, as long as you do a random selection, we'll get an even distribution of the severity that people suffer from migraines from. This does not eliminate the effects of these sources, but it spreads them out so we can see past them. And it protects us from effects that we don't even know about. So again, it's kind of like controlling as much as we possibly can. By randomizing, we're able to see past other things that may have an effect on our response variable because it'll evenly distribute them. The third principle is replicate. You have to repeat the experiment. What this means, not that you have to do the experiment a multitude of times, however that can be beneficial, but it means that you have to apply the treatment to a number of subjects. You can't just give a full dose of the migraine to one person, a half dose to one person, and then no medication to one person. That won't work. What the replication means is that you're going to have multiple people within each treatment group. The fourth principle of experimental design is blocking. So a block is the ability of randomizing to equalize variation across the treatment groups. This works best in the long run. For example, we have 12 kids and want 2 soccer teams of 6 players. 2 of the kids are 12 years old and 10 of the kids are 6 years old. So if we randomly were to assign the teams, and both 12-year-olds end up on the same team, that wouldn't be fair. So what we do instead is we randomly put each 12-year-old 2 different teams, and then we randomly put the 5 6-year-olds on each of those teams. This way we end up with 1 12-year-old on each team and 5 6-year-olds. This makes it more fair in the short run. By doing this, we call the variable, in this case age, a blocking variable. So we're going to block out the fact that age is going to have an effect here. The levels of age are called blocks. Sometimes attributes of the experimental unit we are not studying can have an effect, such as in this case the age. By grouping similar individuals and then randomizing within each block, we can remove some of that variability. Unlike the other 3 principles, blocking is not required in an experimental design. So the other 3 you have to do. You have to control outside influences. You have to randomize, and you have to replicate. With blocking, you only have to use blocking if there is a variable that calls for it. Diagrams of experiments. So it's often helpful to have a diagram of your experiment so you get an idea of what you need to do. So again, helpful to diagram the procedure of an experiment. So the following diagram emphasizes the random allocation of subjects to treatment groups. Then there's separate treatments applied to these groups, and then the ultimate comparison of the results. So we have our random allocation. They're split into 2 groups. We give each group a different treatment, and then we compare their results. Designing an experiment. Completely randomized experiments in one factor are the simplest kind of experiment. For example, an ad for Optigrow plant fertilizer claims that with this product, you will grow juicier, tastier tomatoes. You decide that you're going to test this claim. We know we will need to grow tomatoes, both with and without the fertilizer. So when we're planning this, you want to state what you want to know. We want to know if the tomato plants grown from Optigrow will produce juicier, tastier tomatoes than those grown without Optigrow. Then you have to list your response. So you have to specify what the response variable is and how it will be evaluated. So in this case, we'll evaluate the juiciness and the taste of the tomatoes by asking a panel of judges to rate them on a scale of 1 to 5 in juiciness and taste. Your treatments. So this is where we have to specify the factor levels and the treatments. Our factor is the fertilizer. We're going to have 3 treatments. We'll do 3 plants that get no fertilizer, 3 plants with half the amount of Optigrow, and 3 plants with the full amount of Optigrow. Then you have to specify your experimental unit. In this case, we need 9 plants, so you want to buy 9 plants of the same variety. Then you follow the experimental design, so follow the principles. Control. So you're going to treat each plant the same and control sources of variability you know. They need to be planted in the same area so they get the same amount of light. You need to make sure that you're watering them at the same times and that they're getting the same amount of water and that you're using the same soil. You'll randomly assign, so you'll number your plants and you pick 3 that go into the one treatment group, 3 into the next treatment group, and then the last 3 in the last treatment group. And then you have to replicate. So we're replicating because we're using 3 plants instead of just 1. And then we want to make a picture, so a diagram. And then you have to collect the data. So in the end, you pick a tomato from each plant, have the judges judge them by juiciness and taste. Since you'll have 3 from each category, you can average your results and then compare them. And then, as always, you have to state a conclusion, compare the data, and state what conclusions you have found. Here's an example of the diagram. So we have our 9 tomato plants that we're going to randomly assign to 3 different groups. When you are explaining the experiment, you will have to explain how you would do the random allocation. Then we have 3 different treatment groups, and then we would compare. There should be lines going here to here, but I couldn't make it do it, sorry. We're going to stop here for today. And then we will pick up with this tomorrow. I will see you guys in class. Have a great night.